Hi students, welcome to the extended chapter on triangles. Here in the next slide, we deal with angle bisector segment, internal division. In the picture you see in the slide, an angle bisector divides an angle into two equal measures. Vertex angle P is divided into two equal measures of 20 degrees each. PS is angle bisector segment. The angle bisector divides the opposite side in the ratio of sides containing the vertex angle, that is P. Therefore, PQ by PR is equal to QS by SR. If the angle bisector segment bisects its opposite side, it could be either an isosceles or equilateral triangle. If PS bisects QR into equal measures, it could be an isosceles triangle or equilateral triangle. Angle bisector theorem, external bisector. See, in triangle in the slide ABC, FD parallel to BC, AB is extended to E, AD is extended to C, and by construction, line segment AE is the external bisector of the exterior angle DBE such that BC intersects extended line AD at a point C. Now, by construction, we have extended AB to a point E, AD to a point C. Line segment AE is the external bisector of the exterior angle DBE such that BC intersects extended line AD at point C, as I said. Now, the base AC is divided in the ratio of two of its adjacent sides BA and BD containing the exterior angle in the following ratio: BA by BD is equal to AC by DC. We have drawn FD parallel to BC. Now both BD and BF are transversals to FD and BC. Therefore, angle DBC is equal to FDB and also EBC is equal to angle BFD, corresponding angles. BC bisecting DBE, DBC is equal to angle EBC. Therefore, angle FDB is equal to BFD, making BFD an isosceles triangle. Therefore, FB is equal to BD. Sides opposite to equal angles are equal. In triangle ABC, FD parallel to BC. Therefore, by basic proportionality theorem BPT, we have AC by DC is equal to AB by FB. Now FB is equal to BD, AB is the same as BA. Therefore, AC by DC is equal to BA by BD. Now angle bisector internal division problem. Now in the picture ABC, AD is an internal angle bisector. So AB is equal to 8 cm, AC is equal to 7 cm, BD is equal to 3 cm. Find the length of DC. From angle bisector theorem internal we just went through, we get AB by AC is equal to BD by DC. Thus 8 by 7 is equal to 3 by DC. Therefore 8 DC is equal to 21. Therefore DC length is equal to 2.625 centimeter. Now coming to the next slide, angle bisector external division problem. MNP is a triangle and in MNO, MP is an angle bisector of OMQ. MN is equal to 10 cm, MO is equal to 6 cm, NO is equal to 12 cm. We have to find the length of OP. MP being external bisector by theorem, the ratios we get M1 by MO is equal to MP by PO, which is equal to 10 by 6, which is equal to 10 by 6 is equated to NP by PO. NP is nothing but NO plus OP, that is by OP. Then 12 plus OP by OP is equal to 10 by 6. Cross multiplying, we get 72 is equal to 4 OP. Therefore, OP is equal to 18 centimeter. The midpoint theorem slide next you see, if a line segment joins the midpoints of any two sides of a triangle and which is parallel to the third side, E is equal to half the length of the third side. ABC is a triangle in this picture, and D and E are midpoints of sides AB and AC respectively. If DE is parallel to the third side, BC, then DE is equal to half BC, or 2DE is equal to BC. Now the next slide deals with converse midpoint theorem. The line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side. In triangle ABC, which you see, E is the midpoint of AB, EF parallel to BC. To prove F is also the midpoint of AC. And by construction, draw CM parallel to BA and extend EF such that it intersects CM at D. In triangle AEF and triangle CDF, AB parallel to CM and AC is its transversal. Therefore, alternate interior angles are equal. Angle EAP is equal to angle FCD. Also, AB being parallel to CM, ED is also its transversal. Therefore, angle AEF is equal to angle FDC. E is the midpoint of AB. Therefore, AE is equal to EB. EB parallel to CD. AE is equal to CD. Also, angle AFE is equal to CFD, being vertically opposite angles. Therefore, triangle AEF is congruent to triangle CDF. Thus, AF is equal to FC by CPCT, corresponding parts of congruent triangle. Hence, F is the midpoint of AC, EF parallel to BC. In the next slide, in the given figure, DC parallel to AP and DE parallel to AC. We have to prove that BC by CP is equal to BE by EC. In triangle ABP, DC parallel to AP, BD by DA is equal to BC by CP. Let us keep this as equation 1. In triangle BAC, DE parallel to AC, therefore BD by DA is equal to BE by EC. Keep that as equation 2. Combining equation 1 and 2, BD by DA being common equation 1 and 2, BC by CP is equal to BE by EC, hence proved. Now in the next slide, in the given problem, CD is a perpendicular bisector of AB. Therefore, AD is equal to BD. AE intersects CD at G. We have to prove that CF by CD is equal to FG by DG. Now we have to choose triangle EFC and BDC. These triangles, angle EFC is equal to BDC is equal to 90 degree. ECF is equal to BCD common angle. Therefore, by AA similarity, triangle EFC similar to triangle BDC. Therefore, EF by BD is equal to CF by DC. Keep that as equation 1. In triangle EGF and DGA, EFG is equal to GDA, which is equal to 90 degree. EGF is equal to AGD, vertically opposite angles. Therefore, by AA similarity, EF by AD is equal to FG by DG, equation 2. From equation 1 and equation 2, CF by CD is equal to FG by DG. Since AD is equal to BD, CD being perpendicular bisector of AB. In the next slide, you can see triangle PQR is right angled at R. We have to prove that PE squared plus QD squared is equal to PQ squared plus DE squared. In triangle PER, PE is the hypotenuse. Therefore, PE squared is equal to ER squared plus PR squared by equation 1. And in QDR, QD is the hypotenuse. So QD squared is equal to QR squared plus DR squared, and let's keep that as equation 2. We need to add equation 1 and equation 2 to get to PE squared plus QD squared, which is equal to ER squared plus PR squared plus QR squared plus DR squared. If we combine ER squared and DR squared on the right hand side, it becomes DE squared, the hypotenuse. And if we combine PR squared and QR squared on the right hand side, then it becomes PQ squared as the hypotenuse. Therefore, by Pythagoras theorem, it is proved that PE squared plus QD squared is equal to PQ squared plus DE squared. Thank you. In the next slide, we discuss converse midpoint theorem. If a line is drawn through the midpoint of one side of a triangle parallel to another side, bisecting the third side, then it must be parallel to the base. In triangle ABC, E is the midpoint of AB, EF parallel to BC. To prove F is also the midpoint of AC. By construction, we draw CM parallel to BA and extend EF such that it intersects CM at D. In triangle AEF and CDF, AB parallel to CM and AC is its transversal. Therefore, alternate interior angles are equal. Angle EAF is equal to FCD. Also, AB being parallel to CM, ED is also its transversal. AEF is equal to FDC. E is the midpoint of AB. Therefore, AE is equal to EB. EB parallel to CD. Therefore, AE is also equal to CD. Angle AFE is equal to CFD, vertically opposite angles. Therefore, triangle AEF is congruent to triangle CDF. Thus, AF is equal to FC by CP, CT, corresponding parts of congruent triangles. Hence, F is the midpoint of AC. Therefore, EF must be parallel to BC.